Howdy, Psych92 here, and in this episode we're going to be implementing our synthesis engine. We're going to start by modularizing some of our existing code, then we're going to set up our waveform generation system and then test it, and then finally we're going to finish our synthesis engine by having it process Midi messages to set up our voice structure, which is going to allow it to increment through the waveforms at the correct musical frequency. So in the last episode, we implemented our audio engine and our Midi engine, and what that allowed us to do was send audio via our timer 1 interrupt and also to store and transmit Midi messages as well. And essentially this involved writing some boilerplate code for our peripherals. So our code is already getting kind of messy here, so what we're going to do is modularize it a bit, and we're going to put some of these function calls into some header files, and this way we're going to have less to look at when we're writing our synthesis engine. Alright, so let's begin by creating 3 new files. One will be midi.h, which will store all of our MIDI defines except for MIDI baud rate, since that's of concern to our peripheral setup. And it'll also store our MIDI event struct and the variables we used in our interrupt service routine, and also our USART interrupt service routine itself. The next file we create will be our peripheral setup.h, where we'll store our sample rate, our MIDI baud rate, our timer 1, USART, and SPI DAC functions. Finally, we'll create our sample generation.h, and this is where we're going to be putting our code for generating our waveforms that will be used in our synth. And we'll get into this file more later, so don't worry about putting anything in it now. Now, to use the functions that we put in these header files, we're going to need to include them at the top of our main file. And the order of these is going to be important as well. And now you can see we have a lot less to look at. So like I said, now that we have our code cleaned up, we have less to look at when we're adding new features. So the way the waveform generation is going to work for our synth is that we're going to have an array with 4 different types of waveforms in it, and we're going to be outputting those samples at different rates to achieve different frequencies. Now I imagine that's pretty hard to understand just from hearing that, so let me show it graphically. Alright, so here's that array that I was talking about, and it's cut into 4 sections here. We have a sine wave, triangle wave, square wave, and a sawtooth wave. And it's going to be of length n times 4, where n is the length of one waveform. Alright, so while we have this wave buffer here, which is this array, we're also going to have a pointer called current wave, which is going to point to the first element in the wave buffer, you know, depending on whether it's the sine wave, it'll point here. If it's a triangle, it'll point at n. And the reason that we're keeping this is because when we output our waves, what we're going to do is we're going to use the SPI DAC master transmit function, and then we're going to index current wave at some increment, which is going to go through here. And then we're also going to multiply that eventually by some amplitude value. And what we're going to have to do is we're going to have to make sure that this value, this current wave indexed at increment times amp value, doesn't exceed our 12-bit bit depth of our DAC. So we'll have to pay attention to that later. Alright, so like I said, we're going to be incrementing through this wave buffer here depending on where we're at. And what we're going to do for the increment value is we're going to have it equal to increment plus some value, and then modulo table size so that it wraps around. So it's going to continually, it's going to go 0 to n if we're on sine wave, and then wrap around back to 0, then 0 to n, and continually do that. Okay, so now the length of these sections here is going to correspond to a certain frequency. So if we're incrementing by 1, for example, here, it's going to be whatever frequency that this table size corresponds to. If we were to instead increment by 2, then that would be an octave up from that frequency. So there are 2 big issues with this system. One is that in order to increment by non-octave multiples, so to get musical frequencies that aren't an octave based above this initial frequency that this size corresponds to, we're going to need to increment by floating point value. And we're writing software for AVR, which this particular microcontroller doesn't have a floating point unit. So in order to get that accomplished, what the software needs to do is something called floating point emulation, which is horrendously slow. So we're going to have to come back to that issue and solve it later. So the other issue is that we'd prefer to have this size correspond to the frequency of 20 Hertz, since incrementing by less than 1 is actually going to introduce some harmonic distortion, which is going to not sound great when we're outputting at a frequency that's lower than the frequency that this size corresponds to. And I'll draw an extreme example here. All right, so this is gonna be a super crude example here, but let's say that we have some high frequency here, and when we sample that, it looks like this. And this is gonna be okay for this high frequency because actually what we're gonna have on our DAC output is we're gonna have a low pass filter, which is above twice Nyquist frequency, and then that's going to filter. That's going to smooth out these edges, which that's going to be fine for this frequency. But now, when we try to use this same sample, all these samples for a lower frequency, and we're outputting them slower, it's gonna be. So we're using the same sample here, for example, for however many samples that this is, and it's going to stretch it out, and these rough edges are going to be more noticeable, and that filter is not going to catch these, and it's going to create distortion. I just realized I said the filter would be at twice Nyquist frequency. I brain farted. It's going to be at Nyquist frequency. But hopefully you can see now why we want to store 20 Hertz waveforms. But the issue with that is that storing 20 Hertz waveforms is going to require a lot of samples, and we don't have that much memory. So what we're going to want to do is we're going to want the lowest possible frequency that we can get with the memory that we have. So now hopefully you understand what we're trying to do with our sample generation file. So basically what we're going to do is we're going to want to put those samples, so samples for sine waves, triangle waves, square waves, sawtooth waves, in that wave buffer array at those specific spots. So let's get to actually coding it. So the first thing we're going to do here is we're going to include math.h, since we're going to be needing some of the functions from it. Now we're going to write some defines. The first will be our initial wave frequency, and in other words, that's the frequency that our waveforms are going to be sampled at. We'll use 100 Hertz. Next we'll need our initial wavetable size, which is the size of one waveform in our waveforms buffer. We can calculate this by dividing the sample rate by the initial wave frequency. In this case, our waveforms will be 160 bytes in length. Now as we get into our global variables, we'll allocate our wave buffer on the stack, which will be an array of unsigned 8-bit integers of size initial wavetable size times 4, since we have 4 waveforms. We'll also need to set up pointers to each waveform in the buffer. The sine wave pointer will point to the first memory location in the wave buffer. The triangle wave pointer will point to the wave buffer offset by initial wavetable size, and then the square wave pointer will point to the wave buffer offset by initial wavetable size times 2, and so on. Finally, we're also going to need a pointer called current wave, which points to one of these waveforms. For now, we'll have it point at the sine wave. Now that we have the memory we need, let's start putting the correct samples in these memory locations. We'll start with the easier waveforms, and then I'll explain the sine wave calculation. We'll start with the simplest waveform in terms of code, and that's the sawtooth wave. We'll need a function called generate sawtooth. The sawtooth is basically just a ramp. We'll set a constant float called increment, which will be 255 divided by the initial wavetable size, so that the end of the iteration will reach 255. Now we'll need a for loop that iterates through our sawtooth buffer from 0 to initial wavetable size minus 1. Sawtooth wave indexed at I will be equal to increment times I, which will give us the ramp that we need, starting from 0 and ending at initial wavetable size minus 1. Our next simplest waveform is the square wave, which is what we outputted to the DAC in episode 1. In order for it to be a square wave, it'll need to have a flip point, which flips it from outputting high to outputting low. We'll make it a constant integer called flip point, and we'll set it to the ceiling of the initial wavetable size divided by 2, which will put it in the center, or if the center is a floating point, the next whole number. Now we'll need a for loop to iterate through the square wave buffer from 0 to initial wavetable size minus 1. The logic here will be super simple. If I is less than the flip point, we'll write square wave indexed at I equal to 255, which is the highest value for an unsigned 8-bit integer. Else, write the square wave indexed at I equal to 0. To generate the triangle wave, we'll write a void function called generate triangle. We'll add a constant float called increment, which will define how much we increment by in each sample. These are 8-bit unsigned integers, meaning the highest value will be 255, so we'll take that and divide it by our initial wavetable size divided by 2, since we'll also need to come back down from 255. We'll also add a constant int called decrement point, which will define when we stop increasing the number and start decreasing. This is obviously halfway through the waveform, so initial wavetable size divided by 2. We'll also take the ceiling of that, since we can assure that the first value will be 0, we don't necessarily want the function to accidentally underflow the integer. Next, we'll assure the first value in the triangle wave is 0. A floating point value called temp increment will be used to keep track of the actual floating point value, but we'll round our actual answer. Since we already have our first value, the rest of the waveform will be written to in a for loop that goes from index 1 to initial wavetable size minus 1. If I is less than or equal to the decrement point, we'll increase temp increment by increment and then put the floor of that value in the triangle wave indexed I. Else we decrease temp increment by increment and put the floor of that value in the triangle wave indexed I. Alright, now we're on the sine wave, which is much more difficult to understand compared to the last waveforms. A sine wave looks like this, and it's a pure tone, meaning it only consists of its fundamental frequency. All the other waveforms we've generated so far are made up of many sine waves, and any sound can actually be broken down into many sine waves and cosine waves of differing amplitudes and phases. And a cosine wave is just a sine wave offset by pi over 2. And here is the formula for calculating a sine wave, where A is the amplitude, F is the frequency, T is the time, and theta is the phase. This formula will give us sine wave that peaks at 1 and peaks low at -1, which obviously we're going to have to deal with since we need it to peak high at 255 and peak low at 0. I've copied the formula to a comment here so you can keep it in mind as we do some different things to it. First, let's write the function. First thing that we're going to need to do is convert the frequency into cycles per sample. This is because we need ordinary frequency, or number of occurrences of repeating event per unit of time, and the occurrences that we're concerned with are cycles, and the unit of time is in samples. Now we loop through the sine wave buffer from 0 to initial wavetable size minus 1. And here we're going to have to do some things to fit our sine wave to the parameters we need. First, let's get our basic sine wave going. This right here will give us a sine wave starting at 0 and peaking high at 1 and low at -1. But obviously this isn't what we want. First, let's fix the negative part. We can do this easily by adding 1 to it, which will make it peak high at 2 and low at 0. The issue now is that it starts at 1, which would create a clicking sound when we press the first key. We can fix this too by modifying the phase of the wave so that it starts at a low peak instead. We'll have to offset the phase by 3 pi over 2. Now we have a sine wave that starts at 0, peaks high at 2, and peaks low at 0. Now all we have to do is scale it so that it peaks at 255 instead. This can easily be done by multiplying it by 255 divided by 2. We now have the sine wave we want. We just need to ensure that it's an integer, so we'll use the round function. And that's all of our waveform generation functions. So now all we need to do is call them in our setup code. Let's also make sure that these waveforms work by outputting them to the DAC. An increment variable will be needed to increment through current wave, so we'll make one here and we'll call it timer wave increment. In our setup block, we'll have to call all those waveform generation functions. Remember that this code will be ran before the main loop and before the interrupts start. Our timer 1 interrupt service routine will be used to output our audio, so the rest of the code will obviously be going there. We'll call our SPI DAC master transmit function, and we'll have it output the current wave index at timer wave increment, and we'll multiply that by 16. We're doing the multiplication because we have an 8-bit unsigned integer with a max of 255, but we can output a 12-bit unsigned integer with a max of 4095 to our DAC. So 255 times 16 equals 4080, which is the closest we can get to the max without clipping. And then we'll increment our timer wave increment and use the modulo operator to make sure it wraps around the wavetable. And now we should be getting a sine wave output at 100 Hz. So let's verify that the same way that we did in the first episode. So here's our circuit, and we look over here. Let's see. Yep, that's 100 Hz, and we're definitely hearing a sine wave there. Alright, so now we have our sample generation code complete, but what we need now is a way to process Midi events into the correct increment value for our notes and also the correct velocity for the key being pressed. So this could potentially create some very messy code, so what we're going to do instead is we're going to create a struct called voice, and that's going to make our code more comprehensible, and I'm going to explain that struct and also the code that's going to be used with it before we get to actually coding. Alright, so here's our voice structure. This doesn't have the data types, but we'll talk about those when we get to coding. It has a table position, which is where it currently is in the wave buffer. It has a MIDI note, which is the MIDI note currently being pressed, the actual MIDI value. It has an amp value, which is going to be determined by the velocity, how hard the key is pressed. And then it has a previous notes array, which this is an array of the last notes that were hit, and that's in case, say if we hit multiple notes at once and we let go of one, we want the oscillator to go back down to the note that's still being pressed. And then we also have num notes pressed, which is the number of notes that are pressed, and that's for the same purpose. We use those together. So you probably notice how I skipped the variables starting with increment table, and that's because this is going to require a little bit of explanation. Remember how I talked about how needing floating point values was going to cause an issue? Well, the increment table is how we're going to solve that issue. Well, sort of, because we're still going to need to emulate the floating point values in the very beginning, but then after, you'll see. So let's do a quick example of what I'm trying to do with the increment table. Let's say that we have an increment of 1.2, and we're going to increment 10 times starting from 0. So we have 0, 1.2, 2.4, all the way up to 10.8. So essentially what this means is that we're incrementing by 1.2 samples through our wave buffer. So each sample is 1.2 samples ahead of the next. But of course, this is impossible because we need to index our arrays by integers. So what we'd actually have to do is round these values here. So what we'd actually be doing when we're indexing our array is, instead of 1.2, for example, we'd be actually indexing at 1, at 2.4 we'd be actually be indexing at 2, and so on through all these numbers here. So our actual integer increments, which is what since we're actually indexing at integers, would be, we'd have to move up 1, 1, and then 2 in this case, 1 here, and so on. And this is where the idea of the increment table comes in. What if we could just build this integer increment table here, and we could use this to increment through our array instead of using floating point emulation? And we can sort of do that, and I'll get to the details in a bit. This solution will introduce trade-offs in accuracy and latency. And the latency will be mostly negligible, but let's talk about the accuracy. Now notice that if we add up all the values in our increment table here and then divide it by 10, which is the length of this table, what we're going to get is 1.2, which is exactly the floating point number that we're trying to emulate. So that 1.2 was basically our accuracy, which in that specific case was 100% accuracy. So we would be able to emulate that floating point increment with a size 10 increment table. Now, what if we wanted a smaller increment table? What if we only wanted to use these first 3 values here? So we do the addition and then division by 3, since there's 3 elements here. And what we'd get is 1.3 repeating, which is not accurate and would not give us the frequency that we want. So what if then we, instead of 10, we did 11 elements? Well, in that case, we'd get 1.18 repeating. And that's also not accurate, but it's closer to 1.2 than 1.3. So as you can tell by that example, what I'm about to say is not exactly true. But basically, we're going to treat it like it is. And what I'm going to say is as we grow our increment table, our accuracy is going to increase. So we're going to use this increment table so that we don't need to use floating point emulation in our interrupt. What we really want is as big of an increment table as we can get without running out of memory. So again, we're going to be fighting memory on this one. So hopefully you understood all that stuff that was going on with the increment table. If not, hopefully you'll understand it more when we start actually coding it. But let's get back to the struct and the values that I left out. So again, the increment table is an array which holds our increment table. That should be pretty straightforward after that example. The increment table position is going to hold our position in the increment table. So now we're going to be incrementing through the increment table, which will be incrementing through the wave buffer. So it's a little bit of inception going on there. But again, you'll understand that more when we start coding. This last one here is important as well. Increment table needs proc, which means needs processing. And this is going to be either 0, meaning that we don't need to calculate an increment table, or 1, meaning that we need to recalculate this increment table. And this is going to be important for the purpose of efficiency. Remember that we only need to calculate an increment table once per every note pressed. So if we press a new note, then we do need to process a new increment table. If you remember from the last episode, I said that we were going to be dumping all of our Midi processing onto our main loop. And that's essentially what we're going to be doing in this episode. So first, the main loop is going to check if there's any MIDI values in our buffer that need to be processed. Then it's going to use those MIDI events to update our voice structure. And then after that's done, then it's going to check to see if we need to update the increment table. And if we do, then it'll do that as well. Now, the reason that we wait until after we update the voice structure to process the increment table is that if we press a bunch of notes at once, then it's going to have to process all those increment tables, which that's the most computationally expensive part. So it would be smarter if instead, if we hit a bunch of notes, it went through and updated the voice structure over and over again, which doesn't require much processing, and then the final note that it ends up being, that's the one that the increment table gets processed for. So I know I just dropped a bunch of kind of heady concepts on you just at once there, but like I said, hopefully these things are gonna make more sense when we're coding, which we're gonna get to right now. Let's start by defining our increment table size. We'll set it to 50 for now. Now we're gonna set up our voice structure. We'll type def it too, so we don't need to write struct a bunch of times, just like we did with our MIDI event structs. We'll add all the variables that we talked about when I drew the struct on the whiteboard. Keep in mind that the table position and table increment will be volatile since they'll be written to in the timer 1 interrupt. We'll make the voice struct a global variable named osc for oscillator. We'll also delete that test code we wrote. We're going to need functions to process our MIDI event structs in our main loop and also to process the increment table in our main loop. So let's write some function prototypes. First, we'll write a void function prototype called process MIDI event, which will take in a constant MIDI event pointer to constant data. Next, we'll write a void function called process increment table. Now in our main loop, we're going to delete the MIDI echoing code in our while loop, but we'll leave the incrementing through the MIDI event buffer, and we'll also replace it with the process MIDI event. So this is the block of code that's going to be updating our voice struct. This code should run pretty fast, and if multiple MIDI events are waiting in the buffer, they'll all be overriding each other pretty quickly since we're not processing the increment tables for them. After the voice struct is correctly updated, we'll need to calculate the increment table for it so that we'll be outputting the correct frequency for our timer 1 interrupt service routine. We'll do this by seeing if os.increment table needs proc, and if it does, we'll process the increment table. Pretty straightforward. That's the basic logic that goes into how we're going to be handling MIDI events, but now we have to get into the lower level implementation, which is a little bit hairy. I'll do my best to try to explain as we go along. So let's start with implementing our process MIDI event function. Remember, we're dealing with two different types of MIDI events, note on events and note off events. We're going to handle each differently, so let's write an if-else statement. A note off event can be an event with a note off status byte, or it can be a note on event with a velocity of 0. Yeah, MIDI's pretty weird like that. Remember that this block here is in case of a note off message, and the else block is in case of a note on message. Let's handle the note on message first, since it'll be a bit simpler. The first thing we'll do is set our MIDI note value of our voice strut to data byte 0 of the MIDI event. Next, we'll get our amplitude value from our velocity data byte, and also divide by 8, which since the max of our data byte will be 128, the max amplitude value we could have will be 16, which will allow us to never overflow our 12-bit data and that we need to send to the DAC. Then we'll increase the number of notes pressed by 1. Then we'll add our MIDI note data byte to our previous notes array so that if we are pressing multiple notes, then we can let go of them aside from this one, and our voice will still play this one. Then we'll set our increment table needs processing flag to 1, since obviously we'll need to process this new increment table values for this note later. There's one final thing we need to do with this block. We're going to be interfacing this digital oscillator section with analog hardware. Specifically, we're going to be using it to trigger our analog envelope generator, and to do that, we need to send the envelope generator a gate signal. Basically, a gate signal is high when a note is pressed and it's low when a note is released. Obviously, since this is a note on message, we need to set the gate signal high. We're going to use pin B4 as our gate output pin, so let's go back up to our defines and define gate output pin as pin B4. In our setup code, we're also going to need to configure that pin as an output with data direction register B. Now we're ready to set the pin high in our MIDI note on block, so let's do that by setting port B. That's all we need to do with our note on block, so how about our note off block? The first thing we'll do is decrement the number of notes pressed. Then we have really two possible outcomes. Either we have no notes being currently pressed, or we have notes being currently pressed. We'll handle the simplest case first. If no notes are being pressed, we set the gate output to low. If there are still notes being pressed, let's change the voice structure's current MIDI note value to the previous note and also set the flag that the increment table needs to be processed. Then the voice structure will be outputting the previous note instead. Before we set up our process increment table function, we're going to need to set up some defines, and I'm going to need to explain where the calculations for one of them come from. Okay, well, alright, well, my lapel mic just broke, so I had two options. I had to either put on a gaming headset or use this tiny microphone, and for some reason I thought that using this tiny microphone would look less stupid than the gaming headset, so if you're wondering why I'm speaking into this tiny microphone for the rest of the episode, that's why. So back to the defines. The first of these is going to be the MIDI note defines, and that's going to be pretty simple. Basically, you're going to have a integer value that corresponds to a musical note. For example, if we have 0, that's going to correspond to C0. If we have 1, that's going to be D flat 0, and so on. The next define is going to actually require some calculation, and basically what we want to know is how many cycles per sample should we be outputting. And we're going to do an example with 220 Hertz, which is A3 as a musical note. So if we wanted to know the number of cycles per sample to output for A3, what we would do is we would take 220 cycles per second and divide that by 16,000 samples per second, which was the same thing as multiplying by the reciprocal, and what we end up with is 0.01375 cycles per sample. So that's it, we're done, right? We just have our cycles per sample right there. Well, actually no, because we also have to remember that one cycle of the sample rate, which is what we have here, is not exactly one sample of our going through our wave buffer, because we're iterating through a wave buffer. So we can get how many samples are in that cycle by the same way that we computed our initial wavetable size. So if we take 16,000 samples per 1 second and multiply that by the reciprocal of 100 cycles per second, and of course, you know, the seconds cancel, and what we end up after reducing with is 160 samples per cycle. So that's different. So how do we get the correct value? Well, that's pretty simple actually. Basically what we do is we just take this value and multiply it by 160, since that's how many cycles we have in one sample, or how many samples we have in one cycle, and then what we end up with for this case is 2.2. And this should make a lot more sense intuitively, because if we have 100 Hertz and we want to if we want to increment at 100 Hertz, we'd increment by 1. If we increment by this value, then we're actually outputting a lot less than 100 cycles per second. So 2.2 is obviously going to be a higher frequency than this. So that would be, actually would turn out to be 220 cycles per second. So hopefully those calculations helped you with the code that we're about to write. If I stumbled a little bit, sorry, I'm feeling a little silly with this tiny microphone. First, let's go into our midi.h file and add our MIDI note defines. You can find what values correspond to each note by Googling, or honestly, you could just copy the defines from my GitHub. And you'll really lose nothing by doing that, because you're not learning anything from just typing these in yourself. Now in our sample generation.h file, we'll write our musical note defines. This is another thing I'd recommend you just copy from my GitHub, as long as you know how the calculations work. It's really tedious to do this by yourself. Now that we have those defines out of the way, we're finally ready to write our process increment table code. First, we'll write the function definition. Then we'll need to set up two variables. One will be our running increment, or floating point total, and the other will be increment, which is our floating point value that we'll be adding to our running increment. Now we have a very long switch statement to write. It'll take the current MIDI note, or os.MIDI note, and compare it with all our MIDI note defines, and then match our increment variable to the corresponding musical note define. Here's an example with C0. We do this with each and every MIDI note value, which is super tedious, so again, if you just want to copy this from the GitHub, I don't blame you. Also, it's kind of interesting to note how this is a perfect example of where you'd want to use a switch statement instead of an if-else statement. Aside from it being a lot easier to read, the compiler will also generate a jump table that will make the comparison execution run much faster than if we were to use if-else statements. So now we have our correct floating point increment for our current MIDI note. we'll do essentially the same calculation we did on the whiteboard to generate our increment table values. We'll need a for loop from I equals 0 to increment table size. Inside the for loop, we'll increment the running increment. Then we'll need to get the difference of the rounded running total and the last rounded running total, and we'll put that in the increment table array indexed at I, and that's actually all we need to do to compute our increment table. Finally, we'll set our voice struts increment table needs processing flag to 0 since we just processed it. We just wrote the last bit of our Midi processing code, so now all we need to do is start outputting our waveforms. Let's go into the timer 1 interrupt service routine and delete the code there. We're working with our oscillator voice structure now, so we'll do things a little differently. First, we'll output our current wave indexed at voice struts table position, and we'll multiply that by the voice struts amplitude value. Then we'll update the voice struts table position by adding a value from the increment table indexed at the increment table position to it, and then we'll also use the modulator to ensure that it wraps around. And finally, we'll update the increment table position by adding 1 to it and using the modulo operator to ensure that it wraps around. Now if we upload this to the board, we should be able to play this with any Midi keyboard, like this one right here. Let's test it out. Okay, so cool. We finally have our digital oscillator section outputting musical notes via Midi, but there's a couple things that would be pretty cool to have. One of those would be an LED that shows whenever we're pressing a note if the gate is high or low, and then the other one would be a button to help switch our waveforms so that we can play more than just a sine wave. So let's go into fritzing and add that hardware, and then we'll go into the Arduino IDE and then add some additional code that'll allow us to use that hardware. To set up our LED, we're going to begin by adding a 220 ohm current limiting resistor out of pin B4 or pin 12 as it's marked on the Arduino board. Then we'll add the LED between the resistor and ground, making sure the cathode goes to ground. And that's all we need to do for our LED. Next up is our button. So there's something we need to know about before we set up our button, and that's that when buttons are pressed, they don't go straight from high to low or vice versa. They actually bounce a bit, like in this picture. There are two ways to solve that. One is through software, where you'd basically have a variable that acts as a timer after the state is switched, and the other way is through hardware, where you'd basically use a low-pass filter to make it a smoother transition. Instead of wasting precious processing power, let's fix it in hardware. First we'll connect pin B1 or pin 9 as it's marked on the Arduino to our push button. Then we'll connect the other end of the push button to ground, and we'll attach a resistor from 5 volts to our push button so that when we push the button down, this node will go from 5 volts to 0 volts, and the microcontroller will know that we're pressing a button. The last bit of this circuit will be the part that actually debounces it, and that's the capacitor. We'll add a 100 nanofarad capacitor to our resistor push button node to ground. What we've just done here is create an RC low-pass filter, RC meaning resistor capacitor. All those fluctuations from that diagram will be filtered out and we'll have a much smoother transition. It's still not exactly perfect since we optimally would introduce hysteresis, but it's more than good enough for our purpose. You can look into RC filters for a better understanding of how debouncing is working. Now let's write some code to get our button working. First we'll set up a define for our button. We'll need 2 variables in order for us to switch to our waveforms. The first will be a Boolean value called current wave is selected, which will assure that while the button is being pressed, the synth isn't continually flipping through waveforms. It just selects the next one and then stops. The next variable will be called current wave location, and this value determines which wave will be selected. 0 for sine, 1 for triangle, 2 for square, 3 for sawtooth. In our setup code, we'll need to set up the wave selection pin as an input with the data direction register. In our main loop, we're going to have 2 different cases to deal with. In the first case, the wave selection button has been pressed and the wave selection button wasn't pressed on the last loop. Essentially, if the wave button has just been pressed. In the other case, the wave selection button isn't pressed and a wave was just selected. Essentially, if the button was just released after selecting a waveform. If the first case is true, we need to update the current wave location by adding 1 to it and using the modulo operator to wrap around since we have only 4 waveforms. Then we'll need a switch statement to change the current wave pointer to the correct waveform pointer. Finally, we'll need to set the current wave is selected to 1 since we just selected a waveform. In the case of us just releasing the button after selecting a waveform, we just set the current wave is selected to 0. Alright, so now we should have a LED that flashes whenever we press a note, and we should also have a button that allows us to change waveforms. All right, so let's test it. So the LED is definitely flashing. Let's see about the button. Yep, it's working. There is an issue that, oh my god. There is an issue that if you, when it first starts up, it starts at triangle instead of sine. So the way to fix that real easily and jankily would be to just set it at sawtooth at the beginning. So with that, we've officially finished our digital oscillator section. It's simple but effective, and when we combine it with our analog envelope generator, filter, and amplifier sections, we're going to get some really great sounds out of it. So notice that when we compile the finished code, we still have a tiny bit of wiggle room in terms of memory and performance. And what I want you to do is try to add your own features into that wiggle room. And you could add things like portamento or custom wave shapes or anything else you can think of. So to recap, in this episode, we finished our digital oscillator section by first modularizing our existing code. Then we went ahead and did our sample generation code, and then we processed the Midi events into our voice structure so that we could play musical notes, and then finally we added some additional hardware functionality to it. In the next two episodes, we're going to be getting into our analog sections, so our power supply, envelope generator, filter, and amplifier sections. And the way that we're going to be working on those is we're going to be first simulating the circuits in LT-Spice, which is a circuit simulation software, and then we're going to also be building the circuits on the breadboard, and because of course it's not going to act exactly like the simulation, we're going to see how they work on the breadboard. And I'm not exactly sure which of the sections I'm going to tackle first, so in the next episode I'm not exactly sure of that yet, but I'm thinking it's definitely going to be the power supply and possibly either the envelope generator section or the filter section. Not quite sure yet. I'm pretty excited for the next episode because I've been learning circuit simulation for the last couple of months specifically for this series, and pretty excited to get into that and share that with you guys. And thanks for bearing with me with this tiny microphone. This was a pretty hard episode to do with this microphone, and there was a lot of other disasters that went along the way, so this is probably going to be a really long one. Thanks. I'll see you in the next one.